Let's welcome Professor Yaolin Yi from Nanyang Technological University, Singapore. Professor Yi's research interests include ground improvement, sustainable construction materials, and the treatment of contaminated soils and wastes. He is an associate editor of ASC Journal of Materials in Civil Engineering and the editorial board member of ISEG Ground Improvement Journal. Today, his topic is compression behavior of tire-derived aggregates, TDA. Well, let's welcome Professor Yi.
My name is Yaolin Yi, and I'm from the Nanyang Technological University, Singapore. And today my topic is about compression behavior of tire-derived aggregate, TDA. Here are the outlines. Give me seconds. Okay, including 4 parts: first, background; second, experiments; and the compression estimation and the conclusions. First, background. The problem is that, as we know, the amount of discarded tires is increasing every year, almost everywhere. And the disposal is a problem, like shown in this picture. Here I list some numbers. I just want to highlight one in Canada, because actually I did this research while I was working in Canada in the University of Alberta. Like just in Canada, we have like around 30 million of discarded tires per year. And in Alberta, there's around 5 million. So the problem of the discarded tires include first, land consumption, because it will occupy a lot of land, and especially it has a high risk of catching fire. Here is an example. This happened in 2016 in Spain. Actually, the fire was induced by the discarded tire, and more than 9,000 people excavated. So actually, this is a really big problem, and also it looks really bad. In Alberta, the background is that actually we try to use this material. We mainly use discarded tire to produce tire-derived aggregate, and it's mainly used for landfill drainage application. But this is a very small market. It cannot consume a lot of discarded tires. So on that time, the province tried to find out this and some other ways it can consume natural volume of discarded tires. And especially in Alberta, we have some special type of discarded tires, because in other way, usually the tires are for for cars or trucks. But in Alberta, if you know Alberta, you know that actually it's very famous for oil sand. So there's some special type of tires from the heavy machinery. So it's kind of different. So we also focus on this different type of tires we call off-the-road tires, because it's not used for on the road. It's just off the road. It's for the oil sand industry. So we call it OTR or OTRT. How to produce TDA? Actually very simple. Just cut this discarded tire into small pieces. But you know, if you want high size, like for example, if you want to make it fire, smaller size, it's cost more. So what we can sense is that there are not volumes between these tires, because it's kind of just made from the rubbers, and rubber is easy to deform. So the advantage of this application is that this is not new, but there's still some advantage. The first one, it can consume large quantities of discarded tires, and it also can reduce use of conventional mineral aggregates, and the very low risk of catch fire, because when used in this application, we bury the tire on the ground, so there's less risk of catching fire. And also for civil engineering, the TDA is kind of lightweight, because the unit weight or specific gravity is just like 1/3, even half, or around to 1/3 or half of the conventional aggregate. It can be cost effective because it's made from the waste materials. But of course, it depends on the location. If the transportation is too far away, actually, it's not that cost effective. What the problem we focus on is about compression. And you just see the picture I showed before. This material is kind of very loose, so it will induce very high compression on the loading in civil engineering. So this performance of this behavior actually govern its design and performance. So how to do this? Similar to soil, which is usually we use like one-dimensional compression test to investigate or study the compression behavior, and then we can use it to calculate or estimate the compression in the field. But the problem is that the particle size for this material is much larger compared to soil. For soil, in geotechnical engineering, we use very small odometer test. Like showing here, the diameter just like 50 millimeter and height just 20 to 30 millimeter. So it's very small. I think everyone is familiar with this. But for TDA, it should be very large because the particle size can be higher to 300 millimeter. So we need a very big compression model to do this. And the previous results indicated that actually the size affects a lot. So the problem is that if you want to do the compression test, you need a very big compression model. And also, the loading method is also different. So our objectives of this research focus on the particle size, loading method, initial void ratio, on the compression behavior of TDA. The question we want to answer is very simple. Is it possible to use small-scale laboratory test on small-sized TDA to estimate the compression of large-sized TDA? Because it's quite practical. We cannot always do very large laboratory test in order to calculate the field test result. But this question actually is quite tricky because for soil or rock, it's almost impossible because it's very clear we cannot, based on the one-dimensional compression test of sand, to predict the deformation of rock, right? It's impossible. So, but for TDA, if it's possible, that's what we want to answer because this material actually is simpler. It's just like rubber-tied pieces. So if it's possible, so that's why we want to answer this question. So now I'm going to introduce the experiment. We did 3 types of compression test. One is small-scale laboratory test, relatively small scale. We use small-sized TDA. And the second, we also did the large-scale laboratory test. We used the same TDA as we used in field. And the third one is full-scale field test. So we just use very large size TDA. So we want to compare the result from the 3 types of test and to see if there's something in common, if it's possible to use a relatively small scale test to predict the compression for the large scale. So that's the objective of this research. As I mentioned, we focus on many particle size, initial void ratio or unit weight, and then testing method. Additionally, in our beta, we also investigate the special type of tire source, we call it OTR. These are 2 pictures showing the material. The first one we call it PLTT, so it's passenger and light truck tire. So the normal tires we use on the road. And the second one we call it OTR or OTRT. It's off the road tires. It's used for like heavy machinery, like used for oil sand industry. So the difference is that the second one is much thinner. The first one is very thin. It's very thin. It's like it's plate-like, and the second one is just like rock, right? Looks like the ship. So can we use the same method to predict both materials? So this is another question. And these are the particle size distribution of the materials. So generally, we try different size of materials. And one we call type A. Type A just like has very small size. And second one we type B. So in the small scale laboratory test, we use small sized. And in the field test or large scale laboratory test, we use large size. But additionally, we also test on a very small size. We call type A. This below line. Small scale laboratory test and showing here, it's not small, right? Compared with the automated test, it's not small because the diameter is around 0.6 meter and the height is 1.12. Actually, quite big. But compared to the next one I'm going to introduce, this is relatively small. So for this small scale test, we use particle size. The maximum one just 125. So the diameter is around, it's more than 4 times of the largest particle size. And the loading, we use different load increments. We apply it immediately and then maintain it until the deformation was steady. We don't have water in it, so it's different from the consolidation test for soil. As I mentioned, we focus on different initial water ratio or unit weights. For the large scale, I show here, it's quite large. The diameter is 1.23 meter, and the height is 1.5 meter, and the maximum size is 300 millimeter. So we use exactly the same materials as in the field. And the loading method is different. We do not use the load increments. We use constant deformation rate of 30 millimeter per minute. So remember, the loading methods are different. And because it's quite large, so we only tested on 2 types of sample. One is load sample, second one is compacted samples. This picture, you can see that it's quite large. This is a PhD working for this test. Actually, so far as I know, it was the largest one in the world, because for one sample, we used almost 1 ton of TDA. So it's not convenient to do this large scale compression test. And the third one is field test. Actually, we did a very big excavation pit. The depth is 8 meter, and the width is 17 on the bottom, and on the top is 40 meter. So actually, this is a pilot project. It was for a highway embankment construction. So we use this lightweight field materials. One thing I want to mention is that the soil, the native soil actually is very good. It's quite stiff. So the deformation actually is very small, especially we replace with lightweight material. So the deformation below, in the native ground actually is very small. So for the construction, first we do excavation, and then spread the TDAs, and then compaction, and then just do construction layer by layer. And during this process, I forget something. And we have 2 layers of TDA, and in between we have 1 layer of compacted soil to separate it. And for the lower layer, the bottom layer, we measure the pressures, vertical pressures, as well as the deformation. So we can compare the stress and strain behavior of the 3 types of different tests: small scale laboratory test, large scale laboratory test, as well as field test. So that's the instrumentation. Now I'm going to introduce about the experimental result. Here is the vertical stress and the vertical strain curves for PLTT. We compare 3 types of result: lab test S, small test, lab test L, large test, and field test. What is quite interesting is that in the field, the deformation or the compression is kind of linear. except for the starting point. This point we didn't measure it because the pressure is very small. But it's quite clear. It's almost linear relationship. But for the laboratory test, it's non-linear. And if we compare it, we can see that in the field we have the smallest water ratio. I mean, it has the highest unit weight. So that's the reason it has a very small deformation. So this findings actually agree with other studies because it's very clear in the field we always measure relatively small deformation, but in laboratory we always measure very large deformation. So the key point is the initial state, is initial unit weight or initial water ratio. For example, on this one, the initial water ratio is 1.92, so it has the largest deformation, even at very small vertical stress, around 20 kPa. And another thing is that although we used 3 different types of tests, but we found that as long as the initial water ratio are close. For example, these 2 circles, this one is for large laboratory test. The initial water ratio is 1.38, and the red circular, the initial water ratio is 1.29. So they are kind of close, but there are 2 different types of tests. One small scale, second is large scale, and 2 different materials. One is type B, one is type A. So the particle size are quite different, but we can see that actually the compression or the stress strain curves are quite close. So we also found the same result for the OTR, another type of the test for heavy machinery. Again, the field test, the strain and stress curve is kind of linear. And for 2 type of laboratory test, if the initial water ratio are close, for example, the 2 squares, one is for large scale laboratory test, the initial water ratio is 1.46, and the black square 1.51, also quite close, but they are different type of test. Again, the compression results are very close. And these 2 triangles is similar. Initial water ratio 0.98, and the blue one is 0.92. Again, 2 different types of tests, but the compression curves are quite close. So actually, it seems that the initial water ratio actually control the compression behavior, and the particle size and the loading method actually doesn't affect too much. And this is quite different from what we learned from soil mechanicals, because for soils, the particle size actually matter a lot. And in soil mechanics, we usually plot the water ratio against the vertical stress. So what more interesting is that all the compression curves try to emerge and last. It's indicated they actually have the same law. They follow the same law on the compression. This is for PLTT. No matter the materials, no matter the loading method, no matter the scale. And for OTR, we found the same thing. All the compression curves try to match, try to be together and last. So this was very interesting. And also in soil mechanicals, we usually want to plot it with a semi-scale. So again, I try to match here. This is different from what we know for sand or for clay. For example, for sand, the imaging of compression curve is very difficult unless we have very high stress. For example, here, it seems that they're trying to match, but this is because the soil particles actually has been fractured. So it has been, the soil particles are broken, so they try to get together. This because we have very high content of plastic strain. But for the TDA, most of the deformation is elastic. and they emerge much better compared to here. And for clay, again, it looks like they try to match, but not exactly unless we use normalized water ratio. So the finding means that actually the compression behavior of TDA is simpler compared to soil, compared to sand, compared to clay. So it may be possible we can come up with a simple method to estimate the deformation, vertical deformation, compression. So maybe it's possible to use small-scale laboratory test to predict the compression for large-scale as well as field-scale compression. So in order to do this, we calculate the compression modulus, because this parameter is commonly used for compression calculation. We calculate the compression modulus for very small load increment using this equation, quite simple equation. And I said, it seems that the water ratio is the dominant factor. So we plot it. We plot the compression modulus against the water ratio. What interesting is that all the points actually try to follow the same line, the same curve. So it means different scale of test with different materials, with different particle size, actually they follow the same compression law. So, for example, if we know this function based on some laboratory test, we can simply estimate the compression. So the third part is about the validation of this assumption. The method is very simple. Assume that based on small-scale laboratory tests, we can do regression, get this curve, get this function in terms of compression modulus and the water ratio. And then if we assume the loading is very slow, so we can divide the loading process into very small increment. For each increment, we can calculate the compression modulus based on the water ratio, because we know the initial water ratio. So we can start from the first load increment and to the last one. And then we can modify or correct the modulus according to the corrected water ratio. So then we can start from the first part, from the 0 kPa loading to whatever you want. So to verify this assumption, we use just three samples of small-scale laboratory test on PLTT in laboratory test, which I showed before, just based on the three lines, the three curves, and we do regression. And the R-square not too high, but not too bad, 0.994. So based on this function, we try to predict the result for other tests I just showed you before. And this is prediction for the small scale test, but on OTR. And we can see that the result actually match very, really good. The difference between this OTR and this PLTT is that thickness. The particle size distribution actually is similar, and the thickness is quite different because the tire source is different. So, but what we can see that the prediction is good. So at least the particle size or the thickness doesn't affect our prediction. And then we try to predict the large scale laboratory test. Again, all the results are quite good. The difference between the large scale laboratory test and a small scale laboratory test are that they are different TDA thickness, length, and width. So material particle size are quite different. And the second, the model size are different. And the sample preparation method are also different. Loading method are also different. I mentioned one is we use load increment. And the second one, we use constant loading rate. So this means actually we can use result from the small scale laboratory test to predict the result for large scale laboratory test. So we also try to do prediction for result published by other authors, for other researchers. Again, as long as we know the initial water ratio accurately, the results are not too bad. And we also try to verify the result with field test, not that good compared to result I showed previous, not that good. And the reason is that in the field, actually, we did not know the initial water ratio accurately. We just have some estimated numbers because we do not know the whole volume of the excavation accurately. We also did not know the whole mass. We measured some of them, but there is a very high variation. So this is major reason the prediction is not as good as before. But overall, for civil engineering application, I think it's okay because the difference is between 20% to 10%. So actually, it answered our question. That is, it is possible for this special type of material. It is possible to use small-scale laboratory compression test to predict the result for large scale, for field scale. So we answered this question. Now I'm going to summarize some conclusions. The first one, the compressibility of TDA is primarily dominated by the initial water ratio. And the particle size loading method actually has much less influence compared to the water ratio. This is because this material is quite different from the from soil, because it's a very perfect inelastic materials. I mean the particle, because it's just rubber. So it's easy to deform under deformation. So actually, for example, the clogging interlock for the particles actually is quite small. And second, all different type of TDA samples we studied actually have almost the same compression modulus and water ratio relationship, regardless of initial water ratio, particle size, and loading method. So this is very useful for practice. So we can use this to estimate the compression of large size TDA based on the result of small size TDA in laboratory. So it's possible to apply this method for design. And the next I want to emphasize that, but for field application, one important point is that we need to measure the initial water ratio or unit weight accurately. Otherwise, it won't be very, very high accurate. So that's all for my presentation. And these are some colleagues and organizations I want to acknowledge. And that's all. Any questions?
Okay, thank you. Thank you very much, Professor Yi. And we know that the reviews of TIE can considered as a very potential method in sustainable geotechnical energy. So do we have any questions? If you have some questions, you can raise your hands up, and we can cancel your mute. So no question. Okay, Professor Yi, thank you very much again. And oh yes, we have one question. Yes, Professor Yesla.
Yes.
Hello, thank you for your nice presentation. I have a quick question regarding the laboratory testing. You indicated that the tests were conducted under dry conditions. Exactly. Would you expect different results if there was some moisture in the specimens? If they were saturated or partially saturated?
Actually, it's a good question. And actually, this one paper published in JG, Journal of Geotechnical and Geoenvironmental Engineering, ISEG journal. And this only, so far, I only see one paper published on the consolidation of TDA with the saturated TDA. Others, we all work on the dry TDA because in real application, usually the condition is kind of dry. But to answer your question, I would say based on my experience, it doesn't affect too much because this material has really high permeability. When you compress on the material, the water will come out very quickly. And it may be affect a little bit about the process, but actually it doesn't affect about the final deformation or compression, because it has really, really high permeability. As I mentioned previously in our beta, the application is to use as drainage for landfill. So it means you can think like this way: the permeability is even higher than sand. It's kind of like rock. So in this process, for example, this process for consolidation, like for distribution of excess forward pressure, actually is quite fast. It's very short, so it doesn't affect.
Thank you.
Okay, Professor DNS has also has a question.
Thank you very much for a good presentation. My question is, what is the latest in utilization of rubber tires? Where is the way forward? What's happening?
Excuse me, what is? I didn't hear you perfectly.
What is the way forward in this subject?
With following?
What is the future of these studies? Where are you going to use them?
If you see the field test, actually, let me show you again. We try to solve the problem for the beta recycle because there are a lot of this material produced every year. So the future application, we try to use this as a lightweight material for example, in civil engineering, for road construction, especially if we have some soft ground. If you use this material, the overbed pressure will be very small because the unit weight, you can see it's quite small. So this is for one application. And we solve the problem for the civil engineering. We try to also solve the problem for the environment. We try to use these materials. So reduce, for example, the risk of catching fire, reduce the occupation of the disposal of this material. So that is the future of the material for this as a technology. For example, I mentioned here, actually, for this pilot project, it's very small. It consumes almost 10% of discarded tires in a beta produced 1 year. So if we can use it more in future, it can solve a lot of problems.
Okay, thank you.
Thank you.
Okay, thank you. Thank you, Professor Yi.
Thank you, Prof. Gu.
Okay, well.